everybody for joining us. As you know, you probably saw on the site, we have Praveen with us today to go over sound classification using ML.net. I've been really excited about this one, so I'm going to turn it over to Praveen and enjoy.
Doing the call today and taking time out of your busy schedule on a working day. I appreciate that one. And I'd like to say thanks to Brandon for organizing such a great meetup where we have very interesting talks happening. And today's talk is all about sound classification. So I'll be doing sound classification using ML.net. Okay, so a brief introduction of myself. I'm working as a cloud architect in Harman. It's a Samsung company. The domain I work for is professional audio, video, and control. My area of expertise is cloud and distributed computing. And I'm basically interested in exploring new technologies such as AI, ML, and IoT. I'm based out of Bangalore, India, and a member of .NET Foundation. And just in case you want to see the references for today's talk, everything is available on this URL, short URL. So it will be present on all the slides in case you want to make a note of that one. So this is the agenda for today's talk. I'll be covering basics of sound, then how the sound classification is done, and performing exploratory data analysis on the data that we get from Kaggle. So I took it from the Kaggle, and the framework and tools that we are going to use, then the how we are able to solve the problem of sound classification using ML.NET with a demo. So there won't be a lot of slides, a couple of slides more, then we will directly jump into the demo. So before proceeding, let's understand some concepts that are revolving around the sound that we have. So what is a sound? A sound is a pressure wave created by a vibrating object. So it happens only in through a medium and not in a vacuum. So if there is a vacuum, there is no medium, it won't happen. It is just the amplitude of the vibration that is present in the atmosphere. So we call it as a sound. And the second term is amplitude. So it is the measure of height of a wave or the loudness. So how louder is the sound that we are hearing? It's the measure of that one. Next one is the frequency. This is the total number of waves produced per second. And for a human, it ranges from 20 hertz to 20k hertz. Then next one is your sample rate. It is mainly the how many times per second a sound is sampled. So we take the samples out of a sound waves, and based on those samples, we construct the sound out of that one, or we modify the sound in that one. So the more used or the famous one is 44.1 kilohertz, which is predominantly used by many of the people. So but we have 96 kilohertz that may be applicable to the people who work in studios or professional environment. Then the bit rate. So bit rate is, this is the amount of data transferred into audio. So for example, you want to see how much of data is being transferred. So for that we use, there are different categories of bit rates. You have 8-bit, 16-bit, 24-bit. So which means like you will have 2 to the power 8 or 2 to the power 16, 2 to the power of 24. So the more the number of bits, that means the quality of your sound or the audio will be good. Then the last is the channel. So it represents the spatial experience of sound. Uh, when I say spatial experience, like there are three type of it. One is mono, stereo, and surround. So mono means you cannot figure out from where the sound is coming, whereas in stereo it works in the 180-degree space. That means you will get to know from where the sound is coming within the 180-degree angle. And surround is like a 360 degrees, so it can happen coming, the sound may be coming from the top of your head or from the sides, from the back, anywhere. So it's mainly used within your theaters. Stereo, you can have it in your headphones as well, wherein you can see a effect of a sound coming on one side, not from the other side. So this is because of the two channels where it works on. So stereo is mainly the two channels, mono is one channel. Now, in order to solve the problem of sound classification, we need to see how we can represent a audio file in a different format. So first one is the waveform, which is nothing but a representation of an amplitude with respect to the time. So the x-axis represents the time and the y-axis represents the amplitude. So here it's mainly used in the analog systems and not in the digital system. Whereas the second one is the spectrogram, where we introduced a third uh, spectrum as well, which is called as the frequency. So here the x-axis represents the time, the y-axis represents the frequency, and there is a third one also which is called as the amplitude, which is represented by the depth of the color that we see here. So if the depth is high, that means the amplitude is high. If it is light in color, that means the amplitude is less. So it covers all the three things. Then the third part, third representation is the MEL spectrogram. So it's very much similar to the spectrogram, but the way it differentiates from a spectrogram is spectrograms is more or less a linear thing, and whereas MEL spectrogram works in a logarithmic way. As I just told, like uh, the humans can hear frequencies within the range of 20 hertz to 20k hertz. Then in that case, we use the logarithmic scale for getting those frequencies. So here we plot the things based on the logarithmic scale, not in the linear scales, which gives us more insights within the data itself, what is present in the audio file. Now, this is the sound classification I'm going to do today, and this is how the workflow for that one. So, for example, we have a audio file which is of wave format. So there is a library called as a N audio through which we read the file and its content, and we will get to know the metadata of that file. For example, what is the sample rate, or how many channels is there, whether it is a stereo or a mono, like that. Those kind of things we will get to know through N audio. Now, there is some pre-processing that we can perform on this audio file. So I haven't done that one, but it's possible through on an audio as well. For example, you got a file which is having a sample rate of 44.1 kilohertz, and you want to transform that into a 48 kilohertz. So that is easily possible through an audio. And if you get a file which is a mono file and you want to make it a stereo, then in that case you can make it, or vice versa, you can do it through an audio also. And once this pre-processing is done, we are sure, okay, we need to make the predictions for that one. So before going that way, we will create the MEL spectrogram out of this file content, and that is done by the spectrogram.net library that is present. It's a .NET library. So this will allow us to transform a WAV file to a PNG image. So, and that will represent the MEL spectrogram. So this is the another benefit of having these images or the spectrogram is like these are the ways through which we can visualize what is happening inside a audio file. Otherwise we just need to hear that one, but this is a allow these things allow us to visually uh, see what is present in those, what kind of a frequency is present, what kind of amplitude is present. So those kind of things are present. So spectrogram allow us to create those images. So once the images are created, then it more or less becomes a image classification problem. So for today's scenario, So we will be feeding in these images to a CNN network, and we will be leveraging two things here. So first one is the transfer learning, where we will reuse the ResNet architecture, and the other one is the custom model by using the Onyx format of a file. So once this is done, we will get the classification, and these are the different genre of sound that we have classified for today's problem statement. And based on that, we will get to know what kind of genre is this one. And this is the place where we can see that what all frameworks and tools I have used. So we have used the C# as a programming language, ML.NET as a machine learning framework, a Jupyter notebook for executing these commands and methods. Then .NET Interactive, that is for working with the Jupyter notebook. And N audio is our main library for reading and working with the audio files. It has a lot of features and it's a very good one. It's very old also, but it's a great framework if you want to work with anything related to audio. Then spectrogram.net is mainly used for plotting the spectrogram and MEL spectrogram. Okay. With that, I'll just move on to the demo. Okay. Okay. So I'll be launching the Jupyter notebook. And I consider Jupyter Notebook a better option compared to a Visual Studio because we can explain things, we can put content inside this one, images, anything. Whereas Visual Studio becomes more of like a very raw format of explaining the things. Oops. Okay, here you go. Okay, so this is I've already covered like the basics of sound. How do we visually see an audio file? And this is the workflow that I have done. So before that, I just want to cover up one more thing. There is a very good website where we can see what a spectrogram is. So this is from, I think, Google. So for example, you can see the spectrogram that is being generated, and it's like the time is here, then the frequency. So the higher frequencies at the top side, and the lower frequencies will be at the low bottom. And these colors, the strength of these colors represent the amplitude. Yeah. So this is how we can visually see how audio will look like. So based on the different selections, we can see a different patterns appearing. And this is how we will be able to identify or classify a thing within this one. Just a small thing. Okay. So this is the command for checking what is the version of .NET Interactive. So I'll just make a start on that. And you can see .NET C# is the kernel that I've been using. Now we'll do some exploratory data analysis. This is the place from where I have downloaded the data set for today's problem. Yeah, so it's about music genre classification. So it contains a few things like genre original folder, images original folder, and two CSV file, one for 30-second clip, one for 3-second clip. And it can be seen here. And each uh, folder contains different set of classes or the labels we have. And under this, we have each type of audio file. So generally, this one contains the audio files, whereas this one contains the spectrogram images. So it's a very clean data set. So I need not to construct or make the changes from do the transformation from original wave file to spectrogram. So I can just show you one of them. So this is the data set that gets downloaded. So these are the all audio files, and corresponding to this one, we have the images also, that is the spectrogram files. So here you can see the spectrogram images for those audio files. So if it is not present, then we have to create these files using an audio. That is also possible, but I got this clean data set, so I have just leveraged it for today's problem statement. Here I'm just installing the packages. So I've been using Microsoft.ml, which is your ML.NET package, then Vision API, then analytics, then this is for EDA, exploratory data analysis, and this is for TensorFlow, this is for transfer learning. Then this is the utility that is used for creating the spectrogram or the MEL spectrogram. Then this is the one which I was talking about, the AND audio. And there's an issue with the latest version of 2.1.0. It doesn't work with the .NET Interactive, so I had to downgrade it to 1.9.0, which worked without any issues. These are the namespaces that we have. Yeah. So let me even this. Okay, so all the packages are installed. Now I'll install the audio. These are the packages that I have been using. Here I'm just defining the constants and variables of constants, like what is the model input name, output name, file name. So this is the exported ML.NET model file, which is in the zip format. And if I want to use Onyx format, this is for that one. Then the images are of size 288 by 432. Then this is these all parameters are specific to your MEL spectrogram. fast Fourier transform, size, step size, frequency. So I'll not go deep into these concepts. And this is for the data set what we have. So I have a sample audio file which is of type jazz. So I'll be playing that one. And this is the 3-second CSV file I'll be using for exploratory data analysis. And this is for saving the model file. So and this is for displaying the data frame in a tabular format. So by default, we can't see a data frame in a tabular format. We need to format the table using the formatters. So here we are just registering that Microsoft data frame to be rendered as a table. And these are some utility functions. So for example, here I am playing the audio file by using passing it a file. So, but this is specific to Windows only. I try to use an audio. On audio also supports playing a file and it has full features, but it was not working fine within the .NET Interactive. So I had to use this one. So what it will do is we'll play the audio file, then it will wait for 5 seconds and then stop. This is for displaying the image. So once the spectrogram image is being generated, we can display it inside the notebook using this code. And this is the place where we plot the spectrogram. So it requires a couple of parameters: sample rate. What is the sample rate? Like we talked about 44.1 kilohertz. So it will be 44,000. And audio is it's an array of double, which is nothing but the representation of an audio into a double array, and we get it through the N audio library. And this is the place where we want to save the file. So, and this is the API from the spectrogram.net. We pass in the items to it, then we just add the audio to it. What is the file, that the audio we got from the file. This is for coloring and this is for saving that file. So once the image is saved of a spectrogram, we will leverage that display image to display it. Coming to the MEL spectrogram, there are some issues. For example, it's more or less similar to the spectrogram. So it is doing the same thing. We are creating the spectrogram generator here, passing in it the audio content, and once it is done, there is an API called get bitmap mel, which is nothing but it gives you a bitmap representation of your mel spectrogram, and we just save that one. But the problem here is this bitmap is a Windows specific API and it doesn't work with the .NET Interactive. So I'm not able to utilize this one in the what do you say .NET Interactive or Jupyter Notebook, but we can use these things within our Visual Studio. So, and we saw that we had a data set that is structured as per the classes present in that one. So you have the classes, and then each class folder has its own set of files. But our machine learning pipeline requires the files within the same folder of all the classes. So in order to do that one, I just wrote one utility function that will copy all those things into a one folder. So this is the function that does that. And I think we can ignore this one. This is yeah. Now coming to the loading of data sets. As I told, like data set is available from the Kaggle. I downloaded it, and it contains two CSV files. I can show you. Yeah, these are the two CSV files. So we will use this one for our exploratory data analysis. So we are going to load that file using the data frame.load CSV. So this one will give me the top 5 rows of that data frame. So these are the columns that are present in that file. So, but we are mainly concerned with the file name, length, and the label. So label is the last one where you can see blues. This is the genre that is defined for this file. Then these are some more things from that. So these are the last 5 items. You can see the rock is coming now. Then this tells how many records are there. For example, we have 9,990 records in this, and there is no missing values because everyone is having the same length. Then this will tell us the data type, some variance values, for example, maximum, minimum, and mean, those kind of things for every column. Now, with this, we got to know, okay, these are the number of records and these many files are present. Now, I wanted to see what are the classes present, and I don't want to iterate through the folder, but I want to get it through this CSV file only. So for that, I just had this sound data frame, grouped it by label because label was the last one, and then I'll just get a count of that one. So this will give me all the classes. These are the classes that are present. For example, you have blues, classical, country, disco, hip hop, jazz, metal, pop, reggae, and rock. Now, for analyzing the audio data, I want to see the metadata of my audio file. So for this, I'll be leveraging the N audio. So this is the place where I am using the N audio. This is the class audio file reader, wherein I'll just pass the file name and it will read that file and give me the metadata. For example, sample rate, bytes per sample or bits per sample, then sample count, channel count, and file size. Everything we can get through this object of a audio file reader. And once we have read this file, what we are doing, we are extracting we are reading the full file using the read API and adding it to our audio buffer. So this is our audio buffer that we will be returning. So it is nothing but holds the content of the audio file. So this is how I have chosen for a like jazz file, which I have chosen as a sample file. So it has a sample rate of 22,050. Then number of channels is one, that is some mono file. Bytes per sample is 4. Sample count is, this is your sample rate, and this is the size of the file, 2.5 MB. So now I'll just play the file. So it plays it for 5 seconds and then stops. And using the above utility functions, we are going to plot that as well. So it will create the spectrogram, and it will create the, we will display the image after creating the spectrogram. So this one just creates the spectrogram and saves it to some path. So for example, this is the path where it got saved. Now, this is for the jazz that we have seen. So this is how it looks like, the spectrogram. Now I'll be skipping the mal spectrogram. The reason being it doesn't work. It has some Windows API such as bitmap, which is not compatible with .NET Interactive. So I tried to get it working, but got no success in this one. So I'll just skip this. Now coming to the image classification, uh, the data set that we had, it has images of a audio file in a mal spectrogram format. So basically I'll be using that only. This one is it creates a okay. Now I need to define few things before I make a prediction for any of these things. So what is the size of the my image file, sound image file, that is like 288 by 432, and image data, like it holds information about the image path, and the label means your what is the genre it holds, whether it is jazz or it is a country, like that. And the image input will hold these things only, but it's like a byte array, and it will hold a label as key, as machine learning only works with the numerical data, so we need to use this one. And this is for the image path and the label. And model output is also like it will be holding the image path, label, and the predicted level. So this is the label is the expected level, predicted level is the one that with the our model will predict. So these are some classes that is required for us to work on. And this is the one to display the prediction. So once we have the output, we just display that one. This is a utility function. Now this function allow us to load images from a directory. So we specify the image, and based on that we construct the image data. So what we will do is we will be providing this images original directory name to it, and it will loop through all the subfolders within that one, and based on the class it will create the image data. Now we will be calling that. So in the interest of time, I'm using only 500 record instead of 9990. And after that, I'll just create the ml.net pipeline. So first I need to instantiate the ml context. This is where I'm instantiating it. Then we load the data that we got it structured. Then it will be of a data view type. This is where we will shuffle it. And this is the pipeline that we are creating. So for example, with few input parameters are of string type, for example label, so we need to set it to a label as key. That means what it will do, it will transform that string into a numerical representation. Then we are going to load the images for the whole data set. This is where we will use that one, and this is for training, and after that we will transform that. So this is basically a similar thing what we have for a normal image classification problem in ML.NET. I will leverage the same thing. Then we are going to split the data set. That's a standard practice. Have a better accuracy and better testing of the things of our model. So for example, now in my test set, I have 146 items, whereas in train set, I have 354 items out of 500 that I took. Now defining the architecture and hyperparameters. So I'll be leveraging the transfer learning and using the V2 version of ResNet 50 architecture. The batch size is 10, learning rate is 0.01. And this is how the structure is defined for a ResNet. So we can't modify this one. We can just use whatever is present in as part of the ResNet architecture. Here we have defined the architecture, for example. So this is where I have defined the ResNet V250, And this is for the image classification options that we can set the hyperparameter. I'll be training it for 2 epochs with a batch size of 10 and learning rate of 0.01. And for the validation test set, I'll be passing the test set. And this is the place where we define the image classifier. And here also we will transform it back to the numeric from the numerical representation to the string representation. So, and here we will just train the model using our train data set. So it's gonna take some time, and I leave it running for some time, but I do have another place where I have executed this whole thing. So I can just show it there. So this is the place where I already ran the data set, the model. So for example, it ran for 2 epochs, and in 2 epochs, I got an accuracy of around like 46%. Okay, so it started with 67, then 53, then 61, and then 46. So it's only for 2 epochs and with a very limited data set of 500 images only. I think it's pretty good compared to the data set that we have. So once it is done, we just evaluate it, and based on the evaluation, you can see the accuracy here, 47%, and these are different parameters for multi-class classification. And after that, I just made a prediction. So from the test set, I took an item. So test set had 146 item. What I did is I took the element at the 6th index 6. So I executed that one also, and this is how the output is like. File name was blues, expected genre was blues, and predicted is also genre blues. Whereas if I took another one and made a prediction, it was not correct. So expected was country, whereas the predicted was classical. And once it is done, I just save the model, and the model that I saved, it's okay. Now I think that the session is over, so I couldn't access, but the model size was around like 91 MB. So if we used a ResNet, model came around for 91 MB. Now it is still running, so it will continue to run. So this is with respect to leveraging the pre-trained model of ResNet. I made some changes also. Let me show you. Similar problem I solved using PyTorch, which is available in one of my repo. I have put a link for that as well. Yeah. Yeah. So this is the place where I have any question. Okay, so this is the place where I have solved the same problem using PyTorch, and the benefit here is I was able to train a model and train a model using a custom architecture. Plus here I can show you the different views of different genres. For example, blues have like this, classical has this waveform, so different one is having a different pattern. And this is how the audio is getting identified. This is the spectrogram. This is, then you have the Mel spectrogram. It's different for different type of genre. And the best part here is the architecture. Yeah, so this is the architecture that I have followed, like convolution layer, then batch normalization, then ReLU, then convolution batch normalization. So this is a custom architecture which we can tweak anytime. I have leveraged that one, and once I have trained the model on this one, I saved it and saved it in an ONX format. So this is the place where I have just converted it into ONX format. So this is the file that got saved, soundclassifier.onx. Now I'll be using the same thing in my Visual Studio, the same file. So for example, this is the project that has that file which got generated, and it's around like 23 MB compared to what we had for ResNet, which is 91 MB. And so the execution will start from this place. I have defined where my data set resides, where my audio files are there or image file. And here I have used audio also. Instead of using the image, I'll be using the audio file directly, a WAV file instead of a PNG file. So first I'll show you with the test image file. Then, so this is the main function, just setting what kind of which file to be classified. So first I'll take the image file instead of the audio file. I'm just creating an instance of my custom model classifier. There's a different library here, and I'll start the stopwatch and make a classification, and it will be done on the image file as of now, and I'll print it. So first let me run it, then I'll walk you through the code. Yeah, so you could see here the file that got passed is classical, and the classified sound is classical, so it is matching, that's why it is green in color. Whereas if I give some other file for which the classification is wrong, I'm using hip hop now. We'll see what is the prediction by the model. So for classical, it worked. Yeah. So this was a hip hop file, whereas it has classified it as a classical, which is wrong. So it has misclassified that. Now, same thing I'll do now for the audio files. So let me take the test audio. And here instead of image, I'll be using the audio file this time. Much of change. Yeah, so this time it is a WAV file, audio file, which is being classified as classical. So it's doing a correct prediction here. Let's do it for other one. Hip hop. Yeah. So here also it is classifying it as classical when it is a hip hop. So we could see here that we can give both the image or a audio file as an input, and it will classify it. Now I'll take you to this thing. This class has the real thing. So like this is the sound classifier file, and it has a model input name and model output name, and we could get it directly from the using the Netron using the Netron utility. So when you open this one, it will tell you what is the input name, what is the output name. So this is that one, and this is the asset folder, this is the label, that's all. So I'm just initializing few things inside this one, and this is the thing that is from the N audio. So the execution comes here with the audio file. So it can be your image file, or it can be your uh, audio file. Uh, so I'll just check what is the extension. If it is a audio file and not an image, I'll just use the transformer. It will transform that file into a spectrogram file. So for example, here it will come and it will create the spectrogram. So for creating the spectrogram, we just first need to read the file using an audio. So we'll read that file, and we'll create the content as a double array for that one. Once it is done, we'll create the spectrogram, add the content to that spectrogram, and create the mel spectrogram here. So in this case, I am using a mel spectrogram because it doesn't give me any issue in the Visual Studio. It gives me issue in the uh, .NET Interactive. So for example, here this is the model input name and model output name. So these have to match with the one that we are going to use within our ML.NET pipeline. Otherwise, there will be an error. So once the email spectrogram is created, we will just save it and return the path of that file. So this will give me the file path. So now this one is converting your audio file into a mel spectrogram image. If it is a mel spectrogram image, we will not do this processing. Otherwise, the whole thing is same for both the things. Now what we do, we create a ML context, we'll build a model. So we'll create an empty data. Then this is the transformation that we have to do on any image classification problem. Like we'll resize the images as per the size of the images that were there in the original model. So original model, it was 238 by 432. So we set it to that those values only, and we'll extract the pixels out of that one. Then this is where we load the Onyx model, and this is where we specify the model name. So model is already attached within the project, so it will be available and it can be loaded. So once it is loaded, then we'll just create the model by fitting the data to it. So once the model is created, we will build the input. How we are building, we are taking the input image. So in our case now, it is a mel spectrogram image. We create the image, we create the model input with that, and return it. So once the input is done, then we will make a prediction out of that, so which is done through the prediction engine available in ml.net. So we specify the types of input and output, we specify the model, and we will make a prediction here. So here no training will happen, only the prediction will happen. So this will give us the output, predicted output. From that predicted output, we are just taking the max value and the index of that one. And we already have array of classes which we have loaded from the uh, file that we have label.txt. From this, I have created this classes, and whatever the index we are getting, based on that, we are saying this is the predicted output out of that. So this is how it is done. After that, we are just printing the result. That's all. Nothing more than that. So what is the input file? What is the classified sound? What is the output of that one? So that's all the code that is required to run this thing. And other than that, I have another project here which is specific to .NET Interactive. So whatever commands are the things that I was executing in this, uh, I had the similar things here as well, present here as well. So if in case you need that one, you can just go through that and you will get here like playing an audio. I was using this, then plotting a Mali spectrogram. I was doing this. Everything is, most of the things will be present in Visual Studio as well. Now that is all I have for the demo, but with respect to the references, this is the page where I have put everything. You have, so you got the repo which contains the ML.NET thing, then the slide deck, then sound classification. This is the repo, the current repo, and this is for the ML.NET repo that I have. This is for the notebook. Source code is available here. Then this is for the PyTorch notebook, Onyx model, then the data set. Everything is present here. And these are the two repositories like sound classification ml.net, which has your code, Visual Studio code, as well as your notebook that I walked through. This is the notebook for that. The same is present in your for PyTorch, the model that I created. It's available here. So here, there's no code as such, but you have the notebook file, the model, these two things. So it can be easily accessed and checked. For example, this is your model and the training that happens here, everything. So training is in the case of a custom thing, I have trained it through PyTorch because that flexibility is still not present in ML.NET. But now the good part is like if I want to make any changes in the architecture layers or the hyperparameters, I can just go to this place and make those changes. So these are the layers. I can add more layers, remove more layers, or I can reduce the number of channels, padding. So I can play around with these things, and ultimately it will save it into Onyx format, which I can easily consume inside my .NET project. With that, I think I'm done from my side, and I'm open for any questions. And this is the place where you can find the content. Thank you, everyone. Any questions?
Awesome. That was very, I enjoyed it. It was a great presentation. Thanks so much. I did have a question, like, because when I saw this topic of sound classification, it didn't occur to me of turning it into a spectrogram, turning it into an image, and then doing classification on that. Is this sort of a standard way, or are there some other ways you could do sound classification?
Yeah, that's a great question. Whatever I have researched and looked into the things, it's the standard way. Any of the frameworks I explored, Keras, PyTorch, ML.NET also. So I think Alexander Slot, he has created something similar also for ML.NET. But most of the places, its audio has to be transformed into an image, and it becomes basically an image classification problem. So whatever rules are applicable for an image classification problem will be applicable here also. So this is a benefit that we get. It's kind of a, you can say the knowledge transfer that you get from those things. You can easily utilize that knowledge of image classification and create something with the sound also. It's kind of a standard way.
Very cool. And if I remember correctly, you were doing like 3-second, 5-second chunks of the audio file. Do you ever go any larger than that to try to get better classification?
So for this session, I didn't play around much with the other thing because I got stuck with a lot of other things that I used to get working. So I just leverage whatever is present within the data set, and within the data set, only thing that was present was either a 3-second file or a 30-second file.
Gotcha. Okay.
Yeah. So for example, yeah, these are the two. So one is a 3-second, one is a 30-second file information.
Got it. Okay, cool.
Yeah. Any more question?
All right. Well, if there's no other questions, thank you so much for joining us.
I did have
Praveen.
one comment.
Oh, sorry. Go ahead.
Yeah, please.
Great presentation. I did post a link. I don't know if it made it to you all, but just was it yesterday on the AI show on the Microsoft Developer channel on YouTube? Someone did it audio analytics with Azure Automated ML, which seemed very related. You know, they use a spectrograph approach as well. So timely that both of these came up at about the same time. But thank you. Excellent presentation.
No, thanks for bringing up that. Well, it sounds very interesting. I'll have a look into that one. Thank you.
All right, cool. Well, again, thank you so much, Praveen, for coming and showing us this. This has been very informative to me. Again, after we wrap up, we'll get this posted to our YouTube channel as soon as possible, and I'll post all the links there, as well as that link that was mentioned in the chat. I grabbed that. So again, thanks everybody for joining us. Thank you so much for being here today.
It's a pleasure talking here.
Thank you so much.